Welcome to Module 7, Ethernet Switching. This module gets very concrete and very practical. Ethernet frames, MAC addresses, and how a switch actually decides where to send traffic. This directly builds on Module 6's data link layer concepts and Module 5's hex conversions, both of which come back constantly today. Objective: explain how Ethernet operates in a switched network. Preview the topic table on screen, the Ethernet frame itself, Ethernet MAC addressing, the MAC address table, and switching domain/forwarding methods. By the end, students should understand exactly what a switch does with every frame that hits a port. Ethernet is one of two LAN technologies alongside WLAN, running over twisted pair, fiber, or coax, and spans both the data link and physical layers per IEEE 802.2 and 802.3. Walk the bandwidth progression on screen, 10 megabits per second, up through 100 gigabits per second, and note Ethernet standards define both the Layer 2 protocol and Layer 1 technology together. Same LLC/MAC sublayer split from Module 6, now applied specifically to Ethernet. LLC 802.2 handles communication with upper layers and identifies which Layer 3 protocol is in use. MAC 802.3 is implemented in hardware on the NIC and defines the actual Ethernet frame structure, addressing, and media access. The diagram shows this stack mapping to Ethernet as a technology spanning both Layer 1 and Layer 2. The MAC sublayer has two jobs: data encapsulation, building the actual Ethernet frame, handling source/destination MAC addressing, and the FCS trailer for error detection, and accessing the media. The 802.3 standard covers various physical media types, both copper and fiber. This is the sublayer that actually builds what goes out on the wire. Ethernet frame size ranges 64 to 1518 bytes total. Walk the field table on screen. Preamble/SFD, 8 bytes sync sender receiver. Destination MAC, 6 bytes. Source MAC, 6 bytes. Type length, 2 bytes identifies the upper protocol. 0 by 0800 for IPv4, hexadecimal 86DD for IPv6, hexadecimal 0806 for ARP. Data, 46 to 1500 bytes, padded if needed to hit the 64-byte minimum. And FCS trailer, 4 bytes, CRC error check. This table is worth having students copy down. MAC addresses use hexadecimal, same base 16 system from Module 5's Number Systems module. 1 hex digit equals exactly 4 bits, so a 48-bit MAC address fits in just 12 hex digits. Walk the binary/decimal/hex table on screen if a refresher is needed. Important detail: leading zeros are always shown. Binary 00001010 is written as hex 0A, never just A. A MAC address is 48 bits, written as 12 hex digits, 6 bytes. Every vendor must register with IEEE to get a unique OUI. Walk the example on screen. 00602F3A07BC splits into the left 6 digits, the IEEE assigned vendor OUI, e.g., identifying Cisco, and the right 6 digits, the vendor assigned value, unique per device. A MAC address is also called a burned-in address, BIA, since it's hard-coded into ROM on the NIC. At boot, the NIC copies its MAC from ROM into RAM. Every Ethernet header carries both source and destination MAC. Worth flagging: modern PCs can change their MAC in software. Legitimate uses exist, but it also means MAC-based filtering alone isn't fully secure. Unicast is the simple one-to-one case, a single source device sending to a single destination, both MAC and IP addresses unicast on both ends. Walk the example addresses on screen and the frame structure diagram showing dest MAC, source MAC, source IP, dest IP, and data fields in a clean single path. Broadcast frames get processed by every device on the LAN. The destination MAC is always FFFFFFFFFFF, 48 ones in binary, flooded out every switch port except the one it arrived on. Important scope limit: broadcasts stay within the local broadcast domain and are never forwarded by routers. Multicast sits between unicast and broadcast, received only by devices belonging to a specific multicast group, not everyone, and not just one. Walk the table on screen. IPv4 multicast uses destination MAC prefix 01005E with IP range 224.0.0.0 minus 239.255.255.255. IPv6 multicast uses prefix 33 to 33 with addresses starting FF00. Skeptical smiley face 8. If a switch forwarded every frame out every port like a hub, the network would grind to a halt. Instead, a Layer 2 switch examines its MAC address table to make smart forwarding decisions. Set up the running example: a freshly powered-on 4-port switch with an empty table. Nothing learned yet. This example carries through the next 3 slides. Every incoming frame gets checked for new source information. Continuing the example, PCA on port 1 sends a frame to PCD. The switch sees PCA's MAC isn't in the table yet, so it adds it against port 1. Mention that entries refresh every 5 minutes by default, or get replaced if the same MAC shows up on a different port. Device moved. Next, the switch checks its table for the destination MAC. PCD isn't in the table yet, an unknown unicast, so the switch floods the frame out every port except the one it arrived on, ports 2, 3, 4. Note broadcasts and multicasts get the same flooding treatment, always out every port except the incoming one. PCD replies from port 4. The switch learns PCD's MAC address now too. Since PCA is already known, this reply gets filtered and sent out port 1 only, no flooding needed. With both MAC addresses now known, every future frame between PCA and PCD goes directly to the correct single port instead of hitting the whole network. 2 frame forwarding methods on Cisco switches, contrasted on screen. Store and forward receives the whole frame, computes CRC, discards on error, required for QoS traffic classification like prioritizing VoIP, versus cut-through. Forwards before the frame is fully received, only reads the destination address, lower latency, no error checking. Store and forward trades speed for reliability. Cut-through trades reliability for speed. Cut-through has 2 variants. Fast forward, lowest possible latency, forwards immediately after reading the destination address, occasionally relays errors that the destination NIC has to catch and discard. This is the typical default. And fragment-free, stores the first 64 bytes before forwarding, a middle ground, since most collisions happen within those first 64 bytes, so it catches most errors. Switches buffer frames when the destination port is busy. 2 approaches, contrasted on screen. Port-based memory. Frames queue per specific port. One busy destination can delay unrelated frames even to open ports, versus shared memory. All frames share one common buffer, dynamically allocated per port, supports asymmetric switching, like a 10 gigabits per second server port alongside 1 gigabit per second PC ports. Duplex and speed settings must match between a switch port and the connected device or performance suffers. Full duplex means both ends send and receive simultaneously. Half duplex means only one end sends at a time. Auto-negotiation lets devices automatically agree on the best shared speed in duplex, choosing full duplex whenever both sides support it. Duplex mismatch is one of the most common causes of poor Ethernet performance. Best practice is explicitly configuring both ends full duplex. Historically, connecting devices required choosing the right cable type, straight through for host to switch, crossover for switch to switch, shown in the pinout diagram. Auto 1509 automatically detects which cable type is needed and configures the interface accordingly. With Auto 1509 enabled, default on most modern switches, either cable type just works for almost any connection. Close the module walking each bullet. Frame structure and size range, 48-bit MAC addresses split into OUI and vendor-assigned portions, the 3 MAC address types, unicast/broadcast/multicast, and their patterns, how a switch dynamically builds its MAC table through learning/flooding/filtering, store and forward versus cut-through trade-offs, and memory buffering plus duplex/speed matching with Auto 1509 handling cable type automatically.